Now we will talk about the performance, which is one of the major subjects that you should know when you study computer architecture. And basically, it's the tool that you use to measure how good is your CPU. To introduce the idea of the performance, if you were asked which airplane has the best performance between those four airplanes, one being Boeing 777, Boeing 747, and the Concorde and the Douglas airplanes. To answer this, you should have a different matrix that you can decide based on. So if you measure the passenger capacity, the cruising range, the cruising speed, and how many passenger it transfer times mile per hour. You can see in terms of passenger capacity, the best is Boeing 747. If you care about the cruising range, the best is the Douglas. If you care about the cruising speed, the best is the Concorde. And if you care about the passenger times mile per hour, then you have the Boeing 747. So basically, it depends on what you care about the most. For example, you are only a single passenger and you want to travel as fast as you can, then you should pick the Concorde. If you are a traveling agency and you care about your reporting and you want as many passengers capacity in the airplane as possible, then you should consider the 747. If you want an airplane that is good in all parts somehow, then probably you should consider the Boeing 777. Like it's second here, it's second here, it's also second here, and it's also the second airplane here. So overall, it's like fairly good. If you consider the speed only, the Concorde is the best, but passenger-wise, passenger capacity-wise, it's the worst. So there are many metrics that you should worry about. So now, from this discussion, we should specifically, or we should specify the performance components, and based on that, we can know if a certain CPU is better than another, or at least we have this metric, this number that tells us how good is the CPU. So we will talk first about the response time and the throughput. The response time means how long it takes to do a certain task. The throughput is the total work done per unit time. It could be tasks, it could be transactions per hour. How are response time and throughput affected by replacing the processor with a faster version? They will be, those two, the response time and the throughput, they will be affected this way. If you replace the processor with a faster version, you are decreasing the response time, which almost always improves the throughput. Hence, this will improve both of them. If you add more processors, and this is what we have, more cores, dual core, quad cores, and so on, no one task gets work done faster, so you are not gonna gain anything related to response time. However, the throughput will be sky high. The single user interested in the response time. However, data centers are interested in the throughput or the bandwidth, along with a fairly good response time. For now, we will be primarily concerned with the response time only. We want to make sure that we understand the response time and how is this represented when we talk about the performance. To maximize the performance, we should minimize the response time as we can. Sometimes we call it response time, and sometimes we call it execution time. So to start quantifying this, we will define the performance as 1 over the execution time. If we are comparing two machines, X and Y, or two CPUs, CPU X and CPU Y, then we should find the ratio between their performance. If we get performance X over performance of the machine Y, then we will have this equal to the execution time of Y over the execution time of X. The reason behind this is so simple, actually. The performance of X over the performance of Y is equal to 1 over the execution time of X divided by 1 over the execution time of Y. And this is equal to the execution time of Y divided by the execution time of X, as we stated here. Now, if we get this ratio and the number that we came up with is N, then now we can say X is N time faster than Y. Sometimes you only calculate this part here. We still say the same thing. Since the execution time of Y is the one in the numerator and the execution time of X is the one in the denominator, we would say X is N time faster than Y. Now, these are certain examples, quick examples. If the time taking to run a program is 10 seconds on X and 15 seconds on Y, surely X is faster. It takes less time. So what we did, we found out the execution time of Y, which is the slow machine, divided by the execution time of X, which is the fast machine. We got 15 divided by 10. This is 1.5. So now we can say X is 1.5 times faster than Y. This is when you compare two machines. Now, measuring the execution time, to know it exactly, we have the elapsed time and the CPU time. The elapsed time is the total response time, including all aspects, the processing time, the I/O time, any overhead related to the operating system, or an idle time that you don't do any execution. You calculate all these times and you say that this is going to be the elapsed time. This determines the overall system performance. Now, if we take only one part of it, which is the CPU time, this is specifically the time spent processing a given job on the CPU or inside the CPU. So we take out the I/O time, any other times, for example, the job shares or whatever. It comprises user CPU time and the system CPU time. So it's just the CPU time, whether it's user or system. Different programs are affected differently by the CPU and the system performance. Now, what we will focus on is actually the CPU time And in many of the cases that we are going to study, we would say that the CPU time is the same as the execution time. We will study the CPU clocking, or actually we will look at it because I'm sure at this point you studied somewhere in a previous course. Operation of digital hardware are governed by a constant rate clock cycle. This is tied to, or is the major component of any synchronous sequential circuit. Here we have a clock where the high time is equal to the low time. Basically, this is 50% duty cycle. Anyway, what we care about is the clock period. And you can get the clock period from the rising of the clock to the next rising, and you say that this is the clock period. You could also say that it's from the falling to the next falling, and you get the same clock period. This clock period is usually measured in nanoseconds, which is a very small fraction of the second. And during this clock period, data transfer and computation could happen completely. So a job could be executed and transferred to the memory, or you could load from the memory a value and process on it within this clock period. Now, it's good to know here that if you are dealing with a flip-flop or a latch where you save results, this happens in the rising edge if your flip-flop is rising edge trigger. So it updates the state right here. Now, if we say that we know the clock period as we define it here, this is the duration of a clock cycle. These are some examples. 250 picosecond. Pico is 10 to the power of minus 12. Or you could say it is 0.25 nanosecond, which is equal to this amount. Nano is 10 to the power of minus 9. Now, the clock frequency, which usually what you have, or this measurements, they give it to you with any processor. They say that this processor has this frequency or clock frequency. The clock frequency is the rate, which is how many cycles per 1 second. How many cycles per second? You could get this amount by getting the reciprocal of the clock period. So the clock frequency, these are certain examples like 4 gigahertz, giga being 10 to the power of 9, or 4,000 megahertz. Mega is 10 to the power of 6, which is, for example, 4 gigahertz, as we said, is 4 times 10 to the power of 9 hertz. Now, there is a direct relation between the clock period and the clock frequency. If we say that the clock period, or we wanted to find the clock frequency, then it's going to be 1 over the clock period. So now for the CPU time. The CPU time is the same as the execution time that we talked about. So the performance is improved by many factors. You can get these factors if you know the components of the CPU time. The CPU time is how many CPU clock cycles that you need times the time of each one of them. So it's the CPU clock cycles times the clock cycle time. Or you could say, now you know that the clock cycle time is actually the same as the clock period. So if you take the reciprocal, it's going to be the rate. I should mention here the word rate or clock rate is the same as clock frequency. Similarly, when we say clock cycle time, this is the same as the clock period. And the relation that we discussed between the clock frequency and the clock period, again, could be applied between the clock rate and the clock cycle time. And this is what happens here, actually. We take out the clock cycle time, and instead of that, we have 1 over the clock rate. So now, after we know that the CPU time is how many cycles I have times the clock cycle time, we know that we can improve the performance by reducing this time. And to reduce this time, we can reduce the number of clock cycles, or we could increase the clock rate, or a hardware designer must often trade off between those two to manage the CPU time to make it as low as possible. Now, here is a CPU time example. You have a computer A, which runs in 2 gigahertz clock, and it has 10-second CPU time. So the CPU time is given here, and the clock rate is given. You want to design another computer B, and you are aiming for 6-second CPU time, meaning that you want to reduce the 10 seconds to 6 seconds. You can do a faster clock, but you are paying for this by having the clock cycles increased by 20%, meaning the new clock cycle is going to be 1.2 times the old clock cycles. Now, the question is, how fast must computer B clock, or how fast must computer B clock B to have this, to have these conditions? To do that, we need to find the clock rate of B, which is equal to the clock cycles of B divided by the CPU time of B. We know that the CPU time of B is 6 seconds, and we know that the new clock cycles for this computer B is 1.2 times the old cycles of the computer A. Now, what we are going to find, or the thing that we need to find, is how many, or what is the value of the clock cycles of A to find the clock rate of B, which is the one that we are asked about. The clock cycle of A, based on the equation that we've seen in the previous slide, is the CPU time of A times the clock rate of A. Now, I should mention here that we know that the CPU time is the CPU clock cycle divided by the clock rate. If I want to find the clock rate, then it's going, the relation is like this. The CPU time is equal to the CPU clock cycle divided by the clock rate. Now, if the CPU time is known and the clock rate is known, you can find the CPU clock cycle. If you know the CPU clock cycles and the CPU time, then you can find the clock rate and so on. So here we know the CPU time and we know the clock rate, and we want to know how many clock cycles for A. The CPU time for A is 10 seconds. The clock rate of A is 2 gigahertz, which is going to be 20 times 10 to the power of 9. That's how many clock cycles we have on computer A. Now, this number here, we can plug it right here, as you can see here, and we can calculate the clock rate of B, and we found that the clock rate is going to be 4 gigahertz. So basically, as conclusion, if you want to move from computer A to computer B to satisfy this condition, you have to increase the clock rate from 2 gigahertz to 4 gigahertz to satisfy these needs that you have for computer. Now, we will talk about the instruction count and the CPI. The instruction count of the program, you have a certain program. How many instructions in that program? It's determined by program itself, the instruction set architecture, and also the compiler, because the compiler will convert from the high-level language to the instructions or to the assembly language. The average cycle per instruction, this is what we call the CPI. How many cycles that you are going to spend for every instruction. You should know if you have, for example, let's say the simplest form. You have 2 different instructions. Instruction A, let's call it another letter. We have instruction 0 and instruction 1. Instruction 0, maybe it would need 2 cycles to finish. Instruction 1, maybe it needs more or less than that. So let's consider that it will need only 1 cycle. So if we have millions of instructions or hundreds of thousands of instructions, each one of them will have its own number of cycles that it needs. So what you should worry about is what is the average cycles per instruction. It's determined by the CPU hardware. If different instructions have different CPI, and this is usually the case, then you worry about the average CPI affected by this instruction mix, and we will give a lot of examples about this. Now, we know the clock cycles now is equal to the instruction count times how many cycles per instruction, which is actually, in short, IC for instruction count and CPI for cycle per instruction. So if you want to get how many clock cycles that a certain program needs, then you found how many instructions in the program, and for every instruction of this program, how many cycles you need for that instruction. So you get the count of the instruction times how many cycles for every instruction. IC times CPI. Now, what we are interested in is the execution time. Let's go one step above that. We are interested in the performance. And we know now that performance is 1 over the execution time. Now, the execution time is the same as the CPU time. This CPU time could be calculated by finding how many instructions in a program. We get the instruction count, we multiply it by the CPI, and then we multiply it by the clock cycle time. Looking at this logically, you want to get the time of the CPU. You should count how many instructions in the program, and then every one of these instructions, how many cycles you need to execute that instruction. And then how many time, or what is the time in seconds, usually it's in nanoseconds, for every one of these cycles. If you multiply those 3 together, you will get the CPU time. Just to remember this, and you have it in your mind all the time, you should remember this way. The execution time, which is the CPU time, is equal to the instruction count, which is IC, times the CPI times CCT. Remember it in short this way. Now, we know that the clock cycle time could be rewritten as 1 over the clock rate as well. To understand this better, we have a set of examples. The first one is a CBI example. Let's say we have two computers, computer A and computer B. Computer A, the cycle time is 250 picoseconds, and the CBI is 2. For computer B, the cycle time is 500 picoseconds, and the CBI is 1.2. Notice now we have 1.2 cycle per instruction because we are averaging. So the fraction could happen. Assuming that they have the same ISA and they are running the same program. When we say they are running the same program on the same ISA, this means that the instruction count in computer A and the instruction count in computer B, they are the same. Now, the question is, which one is faster and by how much? You will get the CPU time, which is the execution time for A. And then you get the execution time for B, which is also the CPU time. We get the instruction count, and we will call it I, since it was not given. The CBI is 2 for computer A, and the cycle time is 250 picoseconds. You will get I times 500 picoseconds for A. You do the same for B. Now you call the instruction count here I, because this I and this I for A and B, they are the same. This is what we mentioned in this point. Now you get the CPI of computer B, you put it here, and the 500 picosecond, which is the cycle time, and you get I times 600 picosecond. Don't forget, this is a time. This is time. So the more number you have, it means that you will spend more time to execute in B. And this means A is faster because it has less time. Now, we know from here that A is faster. So answering which is faster, we know that this is A. By how much? You get the ratio, but be careful. You get the CPU time of B, which is the one with more time, divided by the CPU time of A, which is the one with the less time, and we get 1.2. And this means that A is faster, or A is 1.2 times faster than computer B. Now, if we want to talk about CBI, the CBI in more detail, if you have different instruction classes that takes different number of cycle, and this is usually the case, we have certain instruction that deals with the memory. You put them in a class. Sometimes even this class, you divide it into two. Instructions that read from the memory and instructions that write into memory. And you have two different classes. Each one of them have their own CBI. Also, you have other classes, like, for example, the instructions that do arithmetic operation, like addition, subtraction, shifting, and things like this. They could have the same number of cycle per instruction, which is the same CBI. And you can have different classes as well. So if you have n different classes, for each class, you will get its own CBI times its instruction count to get its clock cycle. So you get every one of them, the CBI times its instruction counts, and then you add them together to get the clock cycle. This is what we mean by the summation from I to n. This is assuming that we have n different classes. Now, if we want the CBI, we could have a weighted average CBI. meaning we get the clock cycles that we got here, and we divide it by the instruction count. To do this, you could do it by doing the summations of those different classes. The summation of this term, which is the CBI of that class, times how fraction, or what is the fraction of the instruction, of the instruction count of that class divided by the total number of the instruction. This will give you a percentage, by saying that, for example, the instructions that deals with the memory is 50% of the instructions. And the CBI of them are this much. Then you get this relative frequency, and you multiply it by the CBI to generate the weighted average CBI. That's for one class, only the memory. You get the other class, the other class, the other class, and then you sum them together to get the weighted average CBI. To understand this better, here's an example. You have a compiled code sequence using instruction in classes A, B, and C. So you have three classes, class A and class B and class C. The class A instructions, the CBI of them is 1. For class B, the CBI of class B is 2. And for C, the CBI is 3. Now, the instruction count in two different programs. The first program, we call it sequence 1, and the second program, we call it sequence 2. Now, for sequence 1, we found that the instruction count for the class A is 2. The instruction count of class B is 1, only one instruction. And for class C, there are 2 instructions. In the other program, we have 4 instructions of A, 1 instruction of B, and 1 instruction of C. Now, for sequence 1, we know that the instruction count is 2 plus 1 plus 2, which is 5. For sequence 2, we know that the instruction count is 6. Now, this 5 instructions, let's focus on sequence 1 for now. Those 5 instructions are broken into 3 different classes, 2 and 1 and 2, which is the green bar here. Now, to get the clock cycles, you get the clock cycles by multiplying 2 by 1. So you get every instruction count of the class, and you multiply it by the CBI. 2 times 1, 1 times 2, 2 times 3, and then you add them together. You get 10. Now, this is how many clock cycles that you need for the program. How many cycles per every instruction? It's actually 10 times the instruction, divided by the instruction count, which is going to be 2. So the average, or the weighted average CBI here, is equal to 2. If we get it for the other sequence, you have 6 instructions. The clock cycles 4 times 1, 1 times 2, 1 times 3, and you add them together, you get 9 clock cycles. To get the average, you will divide 9 by 6, which is the total instruction count, and you get 1.5. Meaning, in sequence 1, every instruction, whether it's in class A or B or C, on average will need 2 cycles to finish its job. Now, for sequence 2, every instruction would need 1.5 cycles to finish. So we, instead of saying this every time, we quickly say that the CBI of this first sequence is 2. The CBI of sequence 2 is 1.5. Now, here's another CBI example, which is actually very important. Because it says how to compute the CBI as a weighted average given a certain instruction mix or mix of instructions. So this table tells you that you have 4 classes or 4 types. We have the first type, the ALU, meaning addition, subtraction, ANDing, XORing, things like this. Type B is the loads, which is actually reading from the memory. Type C is the stores, which is actually writing to the memory. And type D is actually the branches. The branches in the instructions is equivalent to the if statements, let's say, in a high-level language. This could be also extended to fors and whiles and things like this. So what we did here, or what we calculated the CBI for each one of the type, and we record it in the table. So type A, CBI is 2, type B, CBI is 2, type C is 3, and type D is 4. We have the frequency of the instruction. So in a program, 50% of the program is going to be type A, 20% type B, 20% type C, and 10% is type D. Now, to calculate the CBI, it's very easy to get the total average or total weighted average CBI. You get it this way. You multiply 2 by 50%, 2 by 20%, 3 by 20%, and 4 by 10%, and then you add them together, as you can see here. And now we know for those classes together, the average or the weighted average CBI is going to be 2.4. Notice that the 2.4 is a number between what you see here. We have 2, 3, and 4. So we have 2.4 somewhere between the 2 and 3. Should be here somewhere. So as a quick check, if you find the classes CBI this way, and the total was somewhere here or here, then you know you are mistaken, because it's a weighted average. Now, as a performance summary, the performance depends on many things: the algorithm, the programming language, the compiler, and the instruction set architecture, or the ISA. The algorithm affects the instruction count and possibly the CBI. And you should think about this. The programming language affects the instruction count and the CBI. So basically, the software affects the same thing: the instruction count and how many cycles per instruction. The compiler affects the instructions count and the CBI. Again, because it's a software, it's affecting the same thing. Only the instruction set architecture affect all of them, which is the instruction count, the CBI, and the CCT, which is the cycle time. The clock cycle time is denoted sometimes to be as TC, which is the time of the cycle. Now, we know, and we mentioned before, that the execution time is the same as the CPU time. And we say that this is IC times CBI times CCT. We could rewrite the same thing this way. The instruction count is actually how many instructions per program. So this is the same as the instruction count. The CBI, actually, by definition, it's how many cycles per instruction, which is the clock cycle per instruction. So this one goes with this one. And the last part here is the clock cycle time, which is how many fractions of seconds per clock cycles. This is the clock cycle time. Now we know how to quantify the performance. By finding the execution time, you can take the reciprocal to get the performance, where the performance is equal to 1 over the execution time. This result is key result. Now, we will talk about the power consumption. The power trends, as you can see in the figure here, starting from this year, on this generation, this is for Intel only, 8286, and then 8386, 8486, then Pentium, Pentium Pro, Pentium 4, and there are many versions of it, all the way up to Core i5 in 2012. You can find that the clock rate was increasing nicely for every generation. These clock rates in megahertz, you could see that they were increasing nicely up to a certain point where you reach 3.6 gigahertz. After that, you kind of get lower and higher, staying the same, let's say. You are in the same line after that year, which is about 2004, 2005, and in the coming years. Actually, the reason you are not increasing the clock rate anymore in new generations after 2005 is because you are facing a power wall. The power consumption was increasing. Every generation, we could increase the power without a problem. Then, after a certain time, we reach to the wall where the power consumption in watts is too high. 100 watts for an integrated circuit is too much. So with the new generation, we try the best to reduce this power. However, with coming of years, we were able to reduce this a little bit, but with time, it's fluctuating back and forth. It's almost a constant. And because of this, we cannot increase the frequency anymore. I could explain this to you in a different way, knowing that one of the components of the power consumption is called the dynamic power. So I'll denote it by the P and D for dynamic power. The dynamic power is calculated by alpha, which is kind of a constant between 0 and 1. It's measured how this integrated circuit or this design, how dynamic it is, how much is it switching. This alpha times the capacitance times the voltage squared times the frequency. And that's what we care about here. Anyway, here's the relation between the power and the frequency. The more frequency you want means that you need to increase the power. However, there was something that balanced this increase and keeps the power constant without changing, meaning that it's constant like this. And this is by either reducing the capacitance or reducing the voltage. If you reduce the capacitance or the voltage, you could increase the frequency with constant power consumption. However, with time, we cannot increase. When I say with time, meaning that with coming new technologies, with new generations, new transistor designs, new technologies, we cannot reduce the capacitance anymore. We also cannot reduce the voltage anymore, or the reduction is very, very small. And because of this, to keep the power constant, we can't increase the frequency anymore. So we have to keep it constant. And that's the constant trend that you see here. And this is also the same reason you can't see big numbers in terms of the frequency of processors. You can't find 10 gigahertz, for example, or 15 gigahertz. Probably you can find 3 gigahertz, 4 gigahertz with boosting and many other aspects in cooling. You could find 5 gigahertz probably, but you cannot exceed that because of this reason. This discussion based on the power, the dynamic power. There is another component of the power consumption called the static power, but this is not the time to discuss this. We are focusing on the computer architecture in this course. Anyway, we say that we cannot increase the clock frequency anymore because of the power wall. Now, reasons for their recent slowing is practical power limits for cooling the microprocessors. Also in the post-PC era, the really critical resource is energy. Energy is tied to power consumption. It's actually the only term, the only thing between them is the time. The battery life trumps all other metrics. Because if you need to consume a lot of power for a device that has a battery, it means it will go off faster. So the battery won't be enough for it if it consumes a lot of power. This is why you see a lot of modes in the new devices or new smartphones where you have a power saving mode. The dominant technology for ICs are the CMOS, which is the complementary metal oxide semiconductor. For the CMOS, the primary source of energy consumption is the dynamic energy that I discussed, and the energy that is consumed when the transistor, it's actually the dynamic energy when those transistors. There are two types, the PMOS and the NMOS. Those transistors, when they switch from 0 to 1 or 1 to 0, they consume energy. As you can see here, the power is equal to the capacitive load, the capacitor, C, times V squared times the frequency. This voltage, it's going down up to 1 volt. The frequency, you have it in giga, and the power, you are reaching about 100 watts, as you can see here. So the capacitive load per transistor is a function of the number of transistors connected to an output. This is the fan out. Also the capacitive of both the wires and the transistors. Actually, in the design of any circuit, you will see the transistor, they are really small in the last layer, and on the top layers, you have a lot of connections. A lot of connections with a lot of wire. So there is capacitance on the wires, and also the capacitance in those little transistors, and they both contribute to the total capacitance, which in turn contributes in the power consumption. What we want is the power consumption as low as possible. The frequency switches as a function of the clock rate. The problem with lowering voltage further, we cannot do it. We are reaching a wall. We cannot lower the voltage. We even cannot lower the capacitance. So we have no choice but to keep the frequency the same with coming new generation. There are other solutions. They are actually like trying to manage the problem and not solve it. To manage the problem, you could increase the cooling, because the idea is very simple here. If the power consumption is increased, the amount of watt is probably more than 100 watt, then you need to cool this integrated circuit or this CPU, because there is a direct relation between the power consumption, P, and the temperature. If there is too much power consumption, the temperature is going to be high. This temperature affects the IC. Sometimes it's reducing its performance, and sometimes it's causing damage or certain errors that cannot be recovered. So to manage this temperature now, we didn't fix the power problem. We managed only the after effect, which is the temperature, and we reduce it by cooling methods. Some cooling methods using fans, or sometimes using liquids. Now, to reduce the power, this is a quick example. Suppose a new CPU has 85% of capacitive load of the old CPU, and it has 15% voltage and 15% frequency reduction. So that's the amount of reduction, meaning that the new voltage is 85% of the old voltage, and similarly for the frequency. So to calculate how many or what is the power ratio here, we will try to get the new power and the old power. If we say that the old power is C times V squared times F, then the new power is going to be 0.85 of the old capacitance, 0.85 of the old voltage, and 0.85 of the old frequency. If you calculate this, you will find that the ratio here is 0.85 to the power of 4, which is 0.52. So that's the power reduction between the new power consumption and the old power consumption. The power wall, we mean by the power wall that we cannot reduce the voltage further, and we cannot remove more heat by cooling methods. So if we are stuck in frequency-wise, we can't increase the frequency anymore, how can we improve the performance? One way is to add more cores. And that's what happens in newer versions of new processors. We have dual core, quad core. Sometimes we have a main processor and a co-processor. So this way we improve the frequency by increasing the throughput. But as we said in this class, we will focus only on the execution time, and we will leave the throughput for other courses. Here is a plot from 1978 all the way to 2014, and we are measuring the performance, which is the instruction count times the CPI times the CCT. This is constrained by power, instruction level parallelism, and memory latency. We will discuss this point after we look at the whole graph. You can see here that in performance-wise, we are increasing the performance, and then we kept increasing the performance in a linear way, and then the performance, we still increase it up to 2012. But the rate of this increase in the old years, it was 25% increase every year. In the middle, it's a very nice increase. About 50% increase per year. In the last years, beginning from 2003 up to 2012, is only 22% per year, which is matching the old years. So that's like a drop in the performance gain in the last years. The reason of this drop is the power consumption. The instruction level parallelism is not as good as before, and the memory latency. One of the major issues is the power consumption. So this is why we move to multiprocessors. You have multi-core microprocessors, more than one processor per chip. It requires explicitly parallel programming, and that's why it's trending, because you want any program to be written in a parallel form where you can distribute it nicely in different cores. If you have core 0 and core 1, only 2 cores, you should write the program so you can run it in both cores at the same time. It compared with the instruction level parallelism. The instruction level parallelism and other type of parallelism, we'll see them in next videos. The hardware executes multiple instructions at once. That's what happens. It's hidden from the programming. What happens is the programmer writes this program the normal way, and the hardware will deal with this parallelism. But it is hard to do. So to reduce this problem, you should do the programming for performance, you should balance the load, and you should optimize communication and synchronization. And these subjects, load balancing, communication, and synchronization, they are subjects that are dealt with in network courses or operating system courses. Now, there is a way to quantify a certain CPU, meaning we want to find its performance. Now, we know that we get the performance by finding the execution time. So the performance is equal to 1 over the execution time. And we know that the execution time, which is the CPU time, is the instruction count times the CBI times the CCT. However, there is a problem because you don't know which program that you should execute. If I have a program, I could write the program so that it runs very nicely in certain machine and runs really bad in another machine. So how to make this fair for all the machines? What we do is we use a benchmark. There is a famous one called SPEC benchmark. The SPEC CPU benchmark, it contains many programs that have different instruction count and different cycles per instructions. It depends on also the machine itself. And in turns, it's affected also by the CCT. However, the major point here is the instruction count. So the SPEC CPU benchmark, there are programs used to measure the performance, supposedly typical for actual workload. It's standardized. The SPEC standing, actually, that it's abbreviated of Standard Performance Evaluation Corp. Those guys developed benchmark for the CPU, for the I/O, and the web, and many others. One of the benchmark that they have called SPEC CPU 2006, and I'm sure they have a more recent one. They have elapsed time to execute a selection of programs. They have negligible I/O, so they only focus on the CPU performance. It consists of a set of 12 integer benchmark and 17 floating point benchmark. Anyway, they have different programs. They have normalized the calculation of the performance using normalized relative measurements to the reference, to a reference machine. And we will show you this in an example. The SPEC ratio here is going to be the execution time for a reference machine The reference machine is actually a machine they chose, and they run all the program on, and there is a recorded execution time for this reference machine. And you measure this, your new machine, based on this old reference machine. So you get the spec ratio by getting the execution time of the reference machine divided by the execution time of the measure machine. Notice that if you're having a new device or a new CPU, the execution time of it should be less than this reference machine, meaning you will gain more spec ratio. The bigger number indicates faster performance. Now, to calculate the spec CPU benchmark, you get what we call a geometric mean. We know the arithmetic mean. The arithmetic mean, we will sum up all the values of the different benchmarks, and then you divide it by the numbers. However, a good measurement is the geometric mean, where you multiply all the execution times of the different programs together, and then you get the root of the degree of n, or basically what you do is you raise it to the power 1 over n. So you get this quantity, the products from I equal to 1 to n, different program. You get the execution time for each one of them, or the execution time ratio, and then you raise it to the power 1 over n. This is if you want to measure the performance. There is also a spec power benchmark. This power measurement, it's actually measuring the server-side Java program operations. So it's basically operation per seconds. And this is going to be the performance. The power, it's in watts or in joules per second. So you get the overall operation per watt this way. You sum up all the operations. There are 11 of them, divided by the summation of the powers. To get a sense of those equations, here is the spec CPU benchmarks, and we run it for Intel Core i7-920. So we want to measure its performance. What happens is we get the different benchmarks, and you find here in this table, we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 different integer programs. So we focused only in the integer. And notice that one of them is interpreted string processing, the other one is related to compression, one of them is a compiler, combinator, an optimizer, a game, a search program, something related to artificial intelligence, a chess game, quantum computer simulation, video decompression, discrete event simulator, finding path, parsing an XML file. Those different programs, they have different instruction count and different CPI, and they have the clock cycle times for each one of them. You can notice that, or you can see that the clock cycle time is the same for all of them. And then you get the execution time, and you also get the reference time. The reference time is the time of the reference machine. You can see that the time is big in the reference machine because it's an old machine. And you get also the execution time of your current machine, which is the Intel Core i7-920, and you get the execution time for all of them. Now, to get this number, we get the instruction count of the Intel Core i7. You basically run those programs. And you know every program has its own instruction count. So you record the instruction count. You know the CPI for your machine, for Intel Core i7-920. So the CPI running this program is this way, and so on for each one. Since you have different programs, you will have different classes of instructions, and based on that, you will have different weighted average CPI. So you record the CPI for each one of them. And you record the clock cycle time. The clock cycle time of the Intel Core i7, it's well known, and this is the clock cycle time. And based on these three numbers, you multiply them by each other, and you get the execution time in seconds. You get the execution time here, here, and here for every one of them. And you know the reference time of this old machine that the guys in spec have chosen, and they record the time for you. Anybody who have a new machine should compare his machine to this reference time by finding the ratio, which is 9770 divided by 508. And you get the spec ratio 19.2. Similarly for this one, and so on. Now you get all the spec ratios. You want one number that tells you how good the Intel Core i7-920. And this number, you get it by multiplying the spec ratios and then raise it to the power of 1 over, count them, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And you get this number, which is 25.7. Also, same observation. Notice that this number is between the lowest and the maximum numbers of these numbers. If we try to get the lowest to this is 15, the lowest up to this point. Oh, there is 14.9. So you have 14.9, and the maximum is 190. And you find out that this number, 25.7, is actually between those two numbers. This numbers tells you that this is the spec ratio of this processor. Now, if you have another machine, it do the same process, and then it gets its number. If their spec ratio, the new machine, let's say it's 24, and the Intel Core i7 is 25.7, now you know that Intel Core i7 is better than this supposedly new machine. And now you know how to compare between different computers or different CPUs. If that CPU that has 24 spec ratio, let's say it has 4 gigahertz processor. And let's say that the Intel Core i7, even though we can get it from here, if you get the reciprocal, you can get how much is its frequency. But let's say, for sake of argument, that it is 3.5 gigahertz. Now, if you look at only this number, you would say that this new machine is better. But in reality, after you do the benchmarking, you found out, no, it's worse. Because this number doesn't tell you everything. It doesn't tell you what happens in the instruction count. What happens in the CPI, which is a very important metric. So if you go buy a laptop, don't look at these numbers only. This doesn't tell you the whole story. Don't look at the processor frequency in gigahertz only. You should run it in a benchmark and see how good your system related to a reference machine. Now, if we want to do the power consumption measurement, what happens is they have a target load, and they have different loads starting from 0%, which you don't have any load, to 100%. And you should notice here that even though you don't have any load, it's 0%, you still consume some power. Because there are things that leaks out of your system, and they consume more power. usually there is a current leakage. Anyway, what happens is for each target load, we calculate how many operations to get the performance, like a measurement about the performance. And you can see the more target load you have, the more operations that you need to execute. So starting from 0 up to 865,000 and something. You also record the average power for each one of them. Like, look at the average power here, it's 80, and then it's increased 120 and so on. The 100% load is will consume 258 watts. To understand the target load, you could imagine that the 100% target load is like you are burning the CPU. You are running the CPU at full capacity. So you will have this much operations, and you will have this much power consumption. Now, to calculate this measurement, which is the summation of the operation divided by the summation of power, you sum up everything here. This is the sum. And you sum up everything in the other column, which is this one. And then you divide this number by this number, and you get how many operations per power. And this is how you get a sense of power versus performance measurement and using spec benchmarks. Now, before we end this chapter, here are some fallacies and pitfalls that we should be aware of. There is a fallacy where we have low power at idle. If you look back at the power benchmark, at 100% is 258, and it's reduced. And you think because we have reduction from 100% to 50%, then if we have 258, we will get half of it in the 50%. It doesn't have to be the case. You can see it's not 50%, it's actually 66% of the peak power. When you go from 100% down to 10%, you think that you will reduce a lot of power. No, you don't. You have 47% of the peak power at this point, not 10%. As the load decreased from 100 to 10%, you actually reduce the power consumption from 100%, which is the 258, to only 47%. So the reduction in the power doesn't decrease at the same rate you are decreasing the load. Part of that because of the static power consumption. Now, the Google data center mostly operate at 10 to 15% load. So the 100% is not realistic. It's only for measurement. Usually, it's between the 10% to 50%. So if we go back here, you can find that the 50%, you consume 170 watts. At 100% load, the 100% load is actually less than 1% of the time. Consider designing processor to make power proportional to load, meaning that the 20% load should use 10% of peak power, but probably this is wishful thinking. So that's one of the fallacies that you should be aware of. The other one, this is a pitfall related to what we call the Amdahl's law. The pitfall is actually expecting the improving of one aspect of the computer to increase the overall performance by an amount proportional to the size of the improvement. This could be impossible. That could never happen. Or in another word, it's wishful thinking. The idea of making the common case fast reminds us that the opportunity for improvement is affected by how much time the event consumes. And we will show you what is Amdahl's law and how does it help us to understand if some improvements are possible or not. Here is an example. Suppose a program runs 100 seconds on a computer. It has multiply operation that is responsible for 80 seconds of those 100 seconds. How much if you were asked, how much do I have to improve the speed of the multiplication if I want my program to run 5 times faster? Here's the wishful thinking here. Is that possible? Is that possible that you run 5 times faster? Now, the execution time of a program after making improvement is given by a simple equation. This simple equation was introduced by Amdahl's, and this is why it's called Amdahl's law. And Amdahl's law is actually, if you want to measure the execution time after an improvement, which is T improved, it's equal to, now we will separate the time into two. The time that is affected by the improvement and the time that is not affected by the improvement. You have a certain improvement factor that reduces this time, which is the time that is affected by the improvement. You divide it by this improvement factor. So we will try to do this or apply the Amdahl's law to the problem that we just mentioned. We have that the execution time after the improvement is actually, now we have 100 seconds in total. So we know that 80 of them, that the one that is responsible for multiplication, and the leftover is 20. So we have 80 and 20. And the wishful thinking that we had, right now we are not sure if it's possible or not. But we want to reduce, or we want to run 5 times faster. Since we want the performance to be 5 times faster, then the new execution time should be reduced from 100 seconds down to 20 seconds only, because 100 is divided by 5, which is the amount of this is the times that we want the new improvement, or how many times we want the computer to be faster. So this is the performance. We want it 5 times faster. So we divide the 100 divided by 5. It's equal to 20. So the improvement is going to be 20 seconds. This is gives us this equation. 20 seconds is equal to 80 seconds divided by n. We want to find how much we want to make this multiply faster to gain this reduction from 100 to 20 seconds. So 80 seconds divided by n plus 20 seconds. Again, I will summarize the whole thing in this point here. We have the total time 100. 80 seconds here. This is the affected by the reduction in multiplication, which is divided by n. We want to find n. And the leftover is 20 seconds. The overall reduction in time, we want the new performance to be 5 times faster. Meaning, instead of the 100s that we have, we want to reduce it to 20 seconds only. Now, to find the n, you can take the 20 to the other side, you will get 0. So, if you want to find n, then you would say n is equal to 80 divided by 0. And this is, you know, mathematically, it cannot be done. So it's actually a wishful thinking. In other words, there is no amount by which we can enhance the multiply to achieve 5 times increase in performance if the multiply accounts for only 80% of the workload. So that's the pitfall. The performance enhancement possible with a given improvement is limited by the amount that the improvement feature is used. Now, another pitfall is taking the million instructions per second, which is the MIPS, as a performance metric. This could cause troubles for you. The MIPS is actually the instruction count divided by the execution time multiplied by 10 to the power of 6, because this is a million, and we are looking for how many millions of instructions per second. Now, the instruction count is the same. The execution time, we break it into the instruction count. The execution time, we know that it is IC times CPI times CCT. The CCT, we can rewrite it as 1 over the clock rate. So this is the instruction count, is the same. The execution time, we take it and we replace it by the instruction count times the CPI divided by the clock rate. And we drop this one the same. Now you can see that we can cross the instruction count with the instruction count, and we end up with the clock rate divided by the CPI times 10 to the power 6. This one is actually very dangerous result. You could think, okay, MIPS is good. I can calculate the MIPS, which is going to be equal to the clock rate divided by the CPI times 10 to the power 6. However, what you are losing if you use this equation, you are taking out the instruction count completely out of the picture. And this could cause some troubles for you, where it gives you wrong information. If you have 2 computers, probably the MIPS will tell you, oh, the first computer is better than the second. However, when you calculate the instruction counts, you found out that it's actually the other way around. So here's the key result, that the CPI varies between programs on a given CPU. Also, the instruction count should be included in the calculation. And this is why we shouldn't use the MIPS as a performance metric. We should use only the execution time. So MIPS is easy to understand. Faster computers means bigger MIPS. But here's the bad thing, or the bad news about the MIPS. They don't account for the capability of the instructions, different ISAs between the computers, instruction count takes it out of the picture completely, and also the difference in the complexity between the instructions. Because of that, we shouldn't use the MIPS as performance metric. As a concluding remark, we talked about many subjects. We should worry about the cost to the performance ratio, and we should make sure it's improving. It's actually due to underlying technology developments. That's the case. We talked about a hierarchical layer of abstraction in both hardware and software in general. We talked about the instruction set architecture, which is actually the interface that resides between the hardware and the software, and we call it ISA. And that's actually the subject of our next chapter. The execution time, this is the best performance measurement. And we say that the execution time is equal to the instruction count times the CPI times the CCT. Once you get the execution time, 1 over the execution time is actually the performance. The power also is a limiting factor. And because of that, we use parallelism to improve the performance meaning we are moving from the execution time to the throughput. These are some metric prefixes for your information. We will see this when we calculate or we have exercises. Kilo is 10 to the power of 3. Mega, 10 to the power of 6. Giga, 10 to the power of 9. Tera, 10 to the power of 12. Peta, 10 to the power of 15. Probably you already hear these somewhere. After that, we have exa, 10 to the power of 18. Zeta, 10 to the power of 21. Iota, 10 to the power of 24. Now going down in the minus or in the negative powers, 10 to the power minus 3, this is milli. 10 to the power minus 6 is micro. 10 to the power minus 9 is nano. 10 to the power minus 12 is pico. 10 to the power minus 15 is femto. And probably you hear these somewhere. I'm not sure about the femto if you hear it or not. Below that, you have 10 to the power minus 18. That's the atto. 10 to the power minus 21 is zepto. 10 to the power minus 24 is yocto. And you can see their symbols, the milli, micro, nano, pico, femto. These are the common ones that we use. Kilo, mega, giga, tera, and beta. And you have the other ones as well. This marks the end of this chapter. And in the next video, we'll talk about the ISA or the instructions.